Answers to quiz number 2. Mark your own. Suppose a forklift, it says raises, ooh, that's a key word. Lifts, that tells me which force we're working against. A 688 kilogram box, 2.4 meters in 45 seconds. How much work is done on the box? Well, work is force times distance. Which force? mg. Which distance? h. In fact, this is partly what led us to that whole work energy theorem. That rule that said another way to think about work was the change in potential plus the change in kinetic. This is what led us to the potential energy equation. It's going to be 688 kilograms times 9.8. TJ, on your test, I'll also, on one question, if I recall, instead of giving you the mass in kilograms, I'll give you the weight in newtons, which means you don't have to multiply it by 9.8. But this time kilograms, so I did. Height, 2.4 meters. Answer, no idea. 688 times 9.8 times 2.4. 16,181.76. I'm going to go 16,200 joules. In fact, really, since 2.4 and 45 Kelly are to 2 sig figs, technically I should go 16,000 joules, but I'm not going to be that fussy. B said, how much power is generated? Well, power is work over time, which is going to be 16,181.76 divided by 45 seconds. Conveniently, TJ, I have this number stored on my calculator, so divide by 45. Do you get 360 watts?
Yes.
Okay. If you're missing units, half mark off. That's the way I roll. Number 2, how much work will I do if I carry an 8.8 kilogram bag 9.3 meters forward? That's not OJ, that's 0 joules. Why 0 joules? This is the piggyback situation. The fact that when you're carrying something, gravity is the force that you're doing work against, and that's vertical, but you're traveling a horizontal distance. Brad, what we're really saying is if you're carrying something or you're piggybacking someone, you're not doing work on that person because their potential energy hasn't changed and their kinetic energy hasn't changed, and our third definition of work was change in potential plus change in kinetic. 0 joules.
Can I just argue because
Go ahead.
Wouldn't their potential energy change?
No, their height hasn't changed.
No, their kinetic energy, sorry.
It all depends. It would depend if I'm at a constant speed, no. There's a split-second change when I go from starting to walking, but once you're giving someone a piggyback, you're not doing work on that object. Okay? In other words, I will say this. If you went 8.8 times 9.8 gravity times 9.3, I'm not giving you the marks for that. It's 0 joules or, I think, nothing. An electric motor develops, okay, here, number 3. They're telling me power, which is work over time. But they're talking, Abe, about force. So I'm going to rewrite that work equation into force times distance over time. And then put your pencils down for 1 second. Physics 12. There is another version of power that comes out of this equation right here. I always show it to kids in Physics 11. I won't be testing you on it. Hey, what are the units for distance? What are the units for time? What is meters per second actually a measure of? Turns out another equation for power is steady force times steady velocity. Physics 12, we use that. Oh, how do you know when to use that in Physics 12? Because they didn't give you a distance or a time, but they gave you a speed. Then you can go force times speed. Anyhow. You can pick your pencils up again. They're asking me to get the F by itself. let's see. So I want the F to stay still. I think the T is going to multiply and the D is going to divide. I think it's going to be power times time divided by distance. It's going to be, careful, not 65 watts, it's kilowatts, 65,000 times time, 35, divided by distance of 17.5. I think this might work out evenly. Yeah, 130,000 newtons. Or 1.3 times 10 to the fifth, and its force, it's newtons. Before you turn the page, trying to think about ways that I could extend this one step further, could I now ask you, what's the maximum mass this motor could raise? Since you know the maximum force this motor can do, how could you go from force to mass in kilograms? Divide by 9.8, right? To go from kilograms to force, you times by 9.8. To go in the other, divide by 9.8. Absolutely. I don't know if I will ask you that on the test, but I just thought of it right now. Usually when I think of something, it's because it's been bugging my subconscious. Maybe I did put it on the test. I don't know. I typed the test up a while ago, and I can't remember all the questions on there. Now, if you get the right answer, full marks. Otherwise, I would probably go something like this. Half mark if I saw that. Probably 1 whole mark if I saw that. And then a half mark for the answer. I'm really more interested. Can you get the concepts? Now turn the page. I sort of like number 4. I sort of like number 4. I sort of like number 4. There's going to be some kind of a stored energy transforming it question on your test. Say what? Well, here's what I mean. 4A, I think, was pretty straightforward, or at least I thought it was, because kinetic energy is equal to a half mv squared, which is 0.5 times. Abe, will I put a 4.2 right there? Say no. Why not? What's that 4.2 measured in? Kilograms. Are you really telling me we have a bullet that weighs 4.2 kilograms? That's a bowling ball. We're not firing bowling balls out of rifles. Abe, my friend, what did I give you the mass in? Look up. Grams. How do I go from grams to kilograms? Divide by 1,000. It's going to be 0.0042 times 965 squared. How many joules of energy? 1,960 joules. What work is done on the bullet if it starts from rest? Well, work is the change in potential plus the change in kinetic. How did you know to go straight to that, Mr. Dueck? Well, actually, I did some thinking. First of all, what I thought to myself was work is force times distance, but I looked at the question and I said, they didn't give me a force or a distance. In fact, I said in part C, they're asking me to find the force, so I don't think force times distance is going to help me. Then I said work is also the area under a force versus distance graph. I don't see a graph. So I said, well, the third definition of work that Mr. Dueck gave me. I also said, I don't think this question suggests that we're firing the bullet into the air or at the ground. I think we're firing it horizontally, which means I think your initial and final height are going to be pretty close to the same. No change in potential. So really what I'm saying is the work is the change in kinetic. Okay, man, what's changing anything? What's changing anything, folks? Final minus initial. That really is worth memorizing. Trust me. What's changing anything? So what's changing kinetic energy? Kinetic energy final minus kinetic energy. See how that kind of flows now? Yeah. Okay. Oh, why can I do that? Starts from rest. Oh, you know what? I know the final kinetic energy. I don't even need to plug in numbers because I figured out the kinetic energy in part A. That's how much work we did. In fact, I have a little Nerf gun here. The way any gun works is somehow you store some energy. A regular gun stores energy chemically in the gunpowder. This stores energy force times distance as a spring. The gun has potential energy. Where is that potential energy going to go? What's it going to get transformed into? Kinetic of the bullet. Yes, some sound, but kinetic of the bullet. So, C. If the work is done over a distance of 0.75 meters, what's the average force? Well, now I can use my other equation for work. I can say, hey, this is force times distance. Now they want the average force. By the way, 0.75 meters, about this long. I think we're talking about a rifle. Yes? So how does a rifle work? That stored chemical energy, when it explodes, creates a cloud of expanding gas inside the barrel. That expanding gas has kinetic energy. It wants to expand out. It runs into the bullet. It pushes the bullet along. That's, Aaron, by the way, why I said find the average force, because I'm pretty sure the force gets smaller and smaller and smaller as the bullet moves along the barrel, because I think since the gas is expanded in the barrel, there's less pressure for it to continue expanding. That's a guess, but that seems reasonable to me, so I had to be physics fussy and say, when I first gave this question, I said, what's the force? And then I said, no, average force. I don't think the force is constant. Okay? Anyhow, I'm pretty sure it's going to be the work divided by the distance, and I conveniently still have this number stored on my calculator, divided by 0.75, 2,610. Oh, not joules, Mr. Dueck, newtons. That's the average force. Probably biggest right when you pull the trigger, probably smallest just as it leaves the barrel, but that's the average. Number 5, a 50-kilogram shell is shot from a cannon at Earth's surface to a height of 4 times 10 to the 2. You know what, TJ? That's 400. What's the potential energy? Okay. Mass times G times 400. 50 times 9.8 times 400. 196,000 joules. How high is it? How high is it? 400. How high is it in part B? 200, which conveniently is half as high. Yes? I could recrunch the numbers, but you know what? If it's half as high, the change in potential energy is going to be that. Or is it? Why am I technically wrong? Aaron. Because, Kayvon, what's change in anything? I'm telling you, your kinetic final energy is 98,000 minus kinetic initial energy of 196,000. You actually, what we're saying is you've lost that much potential energy. You know how I know? You're not as high. Now, if you didn't put a negative there, I'm not going to be fussy this time. I won't take a half mark off, but it is negative. You lost potential energy. Hey, where did that potential energy go? Because it's got to go somewhere. Law of constant. Yeah, that object is speeding up. Probably a tiny bit into air resistance and, bumping into air molecules. But if this, it's a shell, which is pretty aerodynamic and has a lot of mass, it's almost all kinetic still. Oh, how much kinetic energy will it have when it gets to the bottom? You know exactly how much kinetic energy it'll have when it gets to the bottom. 196,000, because all of the potential will now all be kinetic, and that kinetic energy's got to go somewhere. I was listening to a podcast this morning, and I was listening to Neil deGrasse Tyson's podcast. And he was talking about the near asteroid collision from a few weeks ago. One of his favorite movies is the movie Deep Impact. Have any of you seen the movie Deep Impact? So I haven't yet, but apparently I need to because the science is very, very good. It's about an asteroid coming towards the Earth and hitting the Earth. Okay? As part of the plot line, what they managed to do is, unlike Armageddon, where they send space shuttles out there and land on an asteroid, you couldn't land on an asteroid because the asteroid is so small, it has such a small gravitational force that there would be nothing that would suck you onto the asteroid for which you could land, by the way. That's Armageddon, bad physics. But in Deep Impact, what they do as a last resort is they blow up the asteroid into smaller pieces. The problem is that's where their physics, their science went bad. Because when you blow it up, has the mass of the asteroid actually changed? No. Has its speed actually changed? No. So has the amount of kinetic energy that the Earth has to absorb actually changed? No. Blowing it up wouldn't do much good. It would still, even if it burned in the upper atmosphere, the Earth would still have to absorb that energy. It would probably create an atmospheric inferno and kill us all off. Anyways, sorry, what were you going to say?
I was going to argue that because the larger surface area of the explosion.
The only argument, if you had some small pieces that burned off in the upper stratosphere, I think that heat would get radiated out into outer space, and therefore that amount of kinetic energy the Earth would spit back out into space. But blowing up an asteroid just before it hits the Earth won't do any good for the most part because we're still going to have to absorb the energy. Smaller pieces, still, it's going to do as much damage. Spread out over a bigger area, fine.
It might reduce kinetic energy by a lot because even if someone's traveling, like say the school's traveling, if you run a car into the side of the school as it's traveling, the school's still going to keep on going, and velocity won't change much, but there will be a slight push that way for a moment, and then it'll keep on going. So it might slow it.
I think, well, I don't think it would slow it. I think it would deflect it slightly, but it would be a tangent velocity to its initial path. We'll talk. Let's keep going. Because you and I get off on these long, which are great, but the other kids are going, we got to mark. Oh, it's all good physics. Bike rider approaches a hill with a speed of 8.5 meters per second. Okay. The total mass of the bike and rider is 85 kilograms. Okay. Find the kinetic energy of the bike and the rider. Well, $85? Yeah. 0.5 times 85 times 8.5 squared. Squared, Mr. Dueck. I forgot the squared when I wrote it. That was terrible. Do you get 3070.625? 1 mark. He coasts up the hill, assuming there is no friction. At what height will the bike come to a stop? Now, there's 2 ways you can do this. You can say, is there a change in height? Is there a change in speed? This is a job for conservation of energy, because there is. You could say then kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. But then you would say, you know what? My initial potential, I'm starting out on the ground, and my final kinetic, I'm coming to a stop. And you may have just jumped to this statement, Jacob, right away. You may have said, you know what? All of my kinetic initially is going to turn into potential. And then you could have said a half mv initial squared equals mgh final. You could have crossed out the m's, and you could have ended up with h equaling vi squared over 2g, which gets you there. Or you could have said, hey, Mr. Dueck, if 3070 equals mgh, then h is going to be 3070 divided by mg. Either of those will get you there. One's faster, but whatever. It's going to be this divided by 85 times 9.8. He's going to get 3.7 meters high. Suppose an object is traveling at 10 meters per second. What happens to its kinetic energy if we double its velocity? Twice as big? Doug, what? Why 4 times? What if you're traveling 3 times as fast?
9 times.
What if you're traveling 4 times as fast? 16 times. And like I said, that's why there's such a huge difference if you're in an accident at 20 kilometers an hour versus 80 kilometers an hour. 80 kilometers an hour is not 4 times the damage to you and your car. It's 16 times the damage to you and your car. And that's right around where the fatality threshold starts to pretty consistently kick in.
At 80 kilometers an hour? At traveling 80 kilometers an hour or head-on with 2 cars?
We're talking the worst possible scenario, head-on, yeah. Oh, 100 kilometers an hour compared to 20, now you're doing 25 times as much damage. It's the difference between 20 kilometers an hour is what you probably travel in a parking lot. If you bump into a car in a parking lot, you've dinged your car, right? 80 kilometers an hour and you hit something, now we're talking probably physical trauma. Certainly your car is going to be very badly damaged or totaled. Richter scale, by the way, is another one that measures energy, how much damage, but the Richter scale going up by 1 is 10 times bigger. It's a logarithmic scale. So the difference between an earthquake of 5 on the Richter scale and an earthquake of 6 on the Richter scale is 10 times bigger. An earthquake difference between an earthquake of 5 and an earthquake of 7 is, what's 7 take away 5? 10 squared, 100 times bigger. So that's why that Japan earthquake of a couple of years ago that was 8 point something did so much damage compared to a 5 point something. It's 1,000 times. It's 10 to the third times more damage. Yo.
If you say a car is driving,
Yep.
They're both driving at slow speed.
Yeah.
But one crashes into it and gets totaled. Then slipping on ice, so it's 0.
So sorry, say it again.
Okay, car.
Hang on 1 second. Let me pause. One more. Suppose a toy car, blah, 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 blah. What would be its velocity? I see a change in height. I see a change in speed. Oh, it also wants the kinetic energy at the bottom. Okay, first of all, kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. Always got that dead spot in the screen, right about there. There we go. I think our final potential is at the bottom. Our initial kinetic is starting at rest. So the answer to the first question that asks, what is the final kinetic energy? I think the final kinetic energy is just going to be mgh. Is going to be mass 3.5 kilograms. That's a pretty big toy car, Mr. Dueck. Okay, it's a Tonka. It's a big sheet metal monstrosity. Because, yeah, you're right. A toy car should be 3.5 grams maybe, or 15 grams. But we're talking a big sucker. Times 9.8 times a height of 2.3. 3.5 times 9.8 times 2.3. Do you get 78.9 joules of kinetic energy? So there's one answer. Then it wants its velocity. Well, the final kinetic energy is equal to a half mv final squared. So I guess v final is going to be, what, 2 times the kinetic energy divided by the mass, all square rooted, equals 2 times 78.9, all divided by 3.5 and square root of that, times 2 divided by 3.5, square root of that, 6.7, is that right? People nodding? Meters per second. For this question, I'd probably give you 1 mark for that, 1 mark for that, and then if I saw the law of conservation of energy somewhere, I'd probably give you 1 mark. But if you got both answers right, I'd give you 3 out of 3. Okay. I'm actually not going to collect this quiz. I want you to be able to hang on to it to study if you want to study on the weekend, so I'm not going to count this one. That means, Joel, if you didn't do it, you lucked out. But I also think you missed out on a chance to make some mistakes. That's my whole philosophy on these.